So if I take a large number of dice and I just throw it randomly, then I cannot exactly predict which dice is going to be one-sided or two-sided or three-sided or three-faced, but I can know that if I make a large number of measurements, then I will end up getting a probabilities corresponding to each side. Similarly, if I have a large number of hydrogen atoms, then before making a measurement, I don't really know that in each of these hydrogen atoms whether the electron is at a particular energy level or not. Before measurement, I don't really know anything. Before measurement, all the hydrogen atoms exists in a superposition of states. But the moment I make a measurement on each of them, every single hydrogen atom reveals to us that one atom is in a certain state, another atom is in a different state, another atom is in a different state. Hello everyone, welcome back. In this video, I'm going to discuss some of the properties of the separable solutions or the eigenstate solutions of a Schrödinger equation. You see, in the coming lectures, we'll be dealing with a lot of potentials and we'll be trying to solve the Schrödinger equation for different kinds of potentials. But there are certain kinds of properties that will remain same throughout. So therefore, I want to discuss those properties first. For example, stationary states, definite energy levels, how to represent the general wave function solution as a superposition of eigenfunction solutions, what is the idea of probability of a particle being in a particular state, and finally orthogonality. So I'm going to discuss each of them individually so that we get an idea of what we are dealing with, so that we can use these concepts later on when we'll be dealing with different kinds of potentials. So let's first start with the Schrödinger equation itself. So we start with the time dependent Schrödinger equation, which, as you are familiar with, looks something like this: minus h cross square upon 2m del psi del 2 psi upon del x2 plus v psi is equal to iota h cross del psi upon del t. This is the time dependent Schrödinger equation, where psi here represents the wave function solution, and the overall equation basically gives us a solution of any kind of a physical system in quantum mechanics. However, this is a partial differential equation for a particle restricted to 1D, and it is difficult to actually try to solve partial differential equations. So what we are going to do is, we are going to simplify this partial differential equation into an ordinary differential equation. Now, I have done a derivation of something similar in one of my previous videos, where we took a time dependent Schrödinger equation and we used a method called separation of variables method to simplify it to a time independent Schrödinger equation. If you are interested in that derivation, you can take a look at that earlier video. What we have obtained there is that we can simplify this kind of a partial second order differential equation under the condition that whenever we deal with a potential, that potential is independent of time. So many times whenever we are dealing with different kinds of systems, the potentials are independent of time. So if potentials are independent of time, under certain circumstances, we usually apply what is known as separation of variables method, in which we assume that the wave function solution, which is a function of space, which is the x-axis, and time, can be written as a product of a function of x and a function of time together. Now, if I do this kind of an approach here, then this equation becomes an ordinary second order differential equation, which looks like minus h square upon d2 psi upon dx2 plus v psi is equal to E psi. This is also sometimes known as the energy eigenvalue equation. The solution of this kind of a time independent Schrödinger equation is psi x. Now you have to keep in mind that here I am using two different psi here. So this is more like a psi with curly sort of a shape, looking more like a trishul, and this is more like a lowercase kind of a psi. And many times in the literature you will find that we use psi either in bold or a little bit of a curl to it on top of it to represent the actual wave function, and we represent this psi, which is like a lowercase psi symbol, if you can distinguish, as a function of space itself and not the exact wave function solution. So you have to understand the distinction between both of them and keep in mind the context in which I'm using them, because many times when I'm writing it, they look kind of similar, but if you understand that they are actually not the same thing, then it becomes much easier, because the solution of this time independent Schrodinger equation is this lowercase psi, which is essentially known as a eigenfunction. Okay, eigenfunction or eigenstate, or sometimes just the state. This is the solution of the time independent Schrodinger equation, and therefore only a function of space. Now phi here takes the shape of e to the power minus iota Et upon h cross, where E is the total energy of the particle in the system, and this follows from the method of separation of variables that we use to simplify this. And the product of both of this, the function of space and function of time, gives us the actual wave function of space and time. Alright, so this is the actual wave function that we are dealing with. Now in this particular lecture, I simply want to look at the different kinds of properties of the eigenfunction or eigenstate in this particular context, because this methodology is kind of common whenever we encounter different kinds of potentials. As we will see in the coming lectures, whenever we have any kind of a potential V, majority of the time in real life scenarios, we deal with potentials which are independent of time, which are constant with respect to time. In such a circumstance, this is a very common sort of a method that we can use to represent a wave function solution, and by doing that we make our job easier, because now we only have to deal with this time independent Schrodinger equation, which is much more easier to solve. But the moment I apply this methodology, then there are certain kinds of properties that automatically emerge, and those properties I want to discuss today. The first property of these wave function solutions is that they are stationary states. So the first thing that I want to discuss today are stationary states. What do I mean by stationary states? You see, although the wave function overall is a function of distance, space, and a function of time, the probabilities associated with the particle corresponding to this wave function and their expectation values are all constant in time. They do not depend on time. So I can show it to you. So whenever we calculate the probability of any kind of a particle whose wave function is written in this particular manner, then the probability density is essentially equal to this mod square, right? This is something we have become familiar with. What is the meaning of this? The meaning of this is that I take the wave function and I multiply that with the complex conjugate. So if I take this, so this simply becomes psi star x, the eigenfunction complex conjugate e to the power minus iota. So I am going to replace iota with minus iota, because then that would give us the complex conjugate. So this is iota et upon h cross, and then I have again the eigenfunction e to the power minus iota et upon h cross. So you see here that when I do this calculation, these two terms get cancelled out. So what we have remaining is the eigenfunction mod square. So the probability density of the particle being found whenever we have a system where the wave function is written in this particular manner, that probability is independent of time. You see this? It is independent of time. That means the probability density does not change with time. So for example, in our future videos, we are going to look at different kinds of potentials, whether it is an infinite square well potential or a harmonic oscillator or a hydrogen atom. And we will see that the wave function solutions that we actually get, they have corresponding probability densities which are actually independent of time. That means the probability density does not change with time. And as a result, we will also see that the expectation values of different quantities are unchanging with respect to time. So for example, if I find out the expectation value of x, now we know that what is expectation value? We know that in quantum mechanics, the particle could be in a region. It has a spread when it comes to measurements with respect to its position. The average of that spread is the expectation value of position, right? And the way to calculate that is you sandwich the wave function, you sandwich x in between the wave function complex conjugate and the wave function itself, okay, and then you integrate with respect to the minus infinity to plus infinity. So again, I'm just trying to differentiate between the wave function by writing xt here and the eigenfunction just by writing x here, okay, so that there is no confusion. In books, they usually represent the wave function in bold and the eigenfunction in like a normal font. So it is easy to distinguish, but when we write it down, sometimes there might be a little bit of a confusion as to what is what. But if you understand the context in which I'm writing, this is the eigenfunction, this is the wave function. Okay. So if I do again the same thing here, the wave function can be separated into its eigenfunction. So psi x star e to the power iota et upon h cross, and then I have x here, and then you have psi x e to the power minus iota et upon h cross dx integrated between proper limits. Again, these two terms gets cancelled out. All right, so what you have remaining is an integration of psi x star, and then you have x and psi x with respect to dx. You see this expression? No matter what it is, this expression is also independent of time. So when I say independent of time, it simply means that for a given system, this is actually a constant, whatever that is. So if I have some sort of a potential in which the particle exists in, so that the wave functions have these kind of eigenstate solutions, then the average of the positions is going to be a constant in time. It's going to be fixed in time. So even if we assume the particle to be in motion within the potential, the average of the positions come out to be constants in time. Therefore, if I calculate the expectation value of momentum, what is the expectation value of momentum? This is simply mass times the time derivative of the expectation value of position, because this is supposed to represent something that is closer to average velocity. So this comes out to be what? If this is constant, this comes out to be 0. So you see, for particles in which they exist in real life potentials which are independent of time, in those kinds of circumstances, then we can say that the probability densities are independent of time, the expectation values of position are constant, and the expectation values of momentum is equal to 0. Nothing really happens in stationary states, which is kind of very interesting, because we think of a particle in a potential to be in a constant state of motion, especially in the context of classical mechanics. But in the context of quantum mechanics, at least when it comes to the probability densities and the expectation values, they are constants in time. Now the question is, what does this eigenstate solution represent? The eigenstate function represent? You see, whenever we have a differential equation, the differential equation can have solutions in large numbers. You might end up getting a family of curves. So for example, if I take the very simple example of an infinite square wave potential, I end up getting a large number of solutions of the Schrodinger equation. So the question is, what do these distinct solutions represent? You see, a Schrodinger equation for a given system may have a large number of solutions. They can have a large number of different kind of eigenfunction solutions. What do they represent? You see, what they represent is that they are all associated with some distinct energy level. You see, when I talk about an infinite square wave potential, we can think of it classically as a particle being stuck to some kind of a potential well. But the particle could be at rest, or it could be in motion with different kinds of velocities, especially if we think of it in a classical manner. And there is a, you can say, continuous distribution of the energies of the particle that is possible. However, in quantum mechanics, we do not really have a continuous distribution of energies that is possible. We have discrete values of energy associated with the particle. So the particle can be in certain very specific energy levels, which is allowed by the Schrodinger equation. And these energy levels, they correspond to a family of solutions of the Schrodinger equation. So that is what I want to show you in the next point. So these eigenfunction solutions, they correspond to a certain kind of an energy level in which the particle exists in. So if the particle is in one state, it has a certain energy. Particle is in another state, it has a different kind of energy. So if I want to find out the energy of a particle whose wave function solution is known to us, then we use operators, because that's how we do things in quantum mechanics. Whenever you want to find out the physical quantity associated with a particle, then you apply the operator corresponding to that physical quantity onto the wave function solution, and you obtain something called an eigenvalue equation. So the operator corresponding to the total energy of a particle in a quantum mechanical system, that is the energy operator, which is also known as the Hamiltonian. Okay, so the representation of a Hamiltonian operator is simply h cap is equal to minus h cross square upon 2m second order derivative with respect to x plus v. So the energy eigenvalue equation is, if I apply the Hamiltonian onto the eigenstate, then I end up getting the energy eigenvalue associated with that particular eigenstate. Now notice how this is basically the same thing as the time independent Schrodinger equation, right? It's just the Hamiltonian acting on the eigenfunction solution, giving us the energy times the eigenfunction solution. Now, if I want to find out the actual energy of any kind of a particle in any given state, what would I do? Well, I should try to at least find out the expectation value of this Hamiltonian. If I do this, this is nothing but, because we are dealing with stationary states, so I'm just going to write here psi, all right, psi star x, and then you have the operator sandwich between these two things, then you do the derivative. But we know that H acting on psi simply gives us the total energy of the system times psi. So now the total energy of the system is a constant because of conservation of energy principle. So that I can take out of the integration, and I simply end up getting E psi star psi dx. Now because these eigenfunctions are normalized, we actually end up having to take these kinds of assumptions that the states should be normalized, because otherwise the Born's statistical interpretation would not be valid, right? The particle being found in the entire universe along the x-axis should always come out to be equal. The probability should come out to be equal. So this comes out to be 1. Therefore, this is nothing but E, all right, which is kind of interesting. The expectation value of the energy for a system or a particle in a particular eigenstates, a solution is actually nothing but the total energy of the system. Okay, fine. Now let's take a look at h square. Now why I'm taking h square, I'm just going to come to that in a moment. Let's just first look at it. Okay, so again I find expectation value of h square, in which I act h twice onto psi, because that's how we do it. You operate it twice onto psi. Now what happens when you operate h onto psi? You end up getting e psi. But what happens when you operate it twice? Then essentially you actually end up getting, so I take out e here, I apply it first, I get e psi, I take e out of the integration, and I actually end up with psi star h cap psi dx. Now again h Hamiltonian is acting on the psi, I again get e psi, so I take the e out and I end up getting e square. E square integration of psi star psi dx, because psi is normalized, this is nothing but e square. Now what I wanted to find out was, I wanted to find out del h, or I should say del e, which is basically, I mean, if you look at it in terms of a statistical system, the standard deviation of the spread of the energy. Okay, so this comes out to be h square expectation value minus h expectation value square root over. Now there is something that is very interesting that is happening here. If I find out the standard deviation or the spread of the energies for this particular system, then this is just a standard formula, root over h square expectation value minus square of the expectation value of h. This simply comes out to be nothing but e square minus e square root over, which is equal to 0. Now what is the meaning of this 0? The meaning of this 0 is that the energy of the particle in the quantum mechanical system has 0 spread. Let me repeat that again. If there is a particle in a quantum mechanical system that is in a given eigenstate, let's suppose psi, because as I just now said, the Schrodinger equation can have a large number of psis or large number of eigenstate solutions, a family of curves, so to speak. But if the particle is in one of those states, then it has a 0 spread in terms of energy. That means that state is associated with a fixed energy level. All right. Now we know that whenever a particle is in some kind of an eigenstate, its position may have a spread, its momentum may have a spread, but the energy has 0 spread. Which means every single state in a quantum mechanical system is associated with a definite energy level. So if I have a system whose Schrodinger equation gives me large number of eigenstate solutions, so let me say that I have a solution psi 1, I have a solution psi 2, I have a solution psi 3, I have a solution psi 4. By the way, this is what happens later on whenever we are going to deal with infinite square wave potential or hydrogen atom or harmonic oscillator. We will see that theoretically there are infinite number of solutions of the Schrodinger equation, and we can call them as psi 1, psi 2, psi 3, psi 4, whatever. But all these distinct states correspond to certain distinct energies. So psi 1 means that the particle has energy, let's suppose E1. Psi 2 means that the particle has energy, let's suppose E2. Psi 3 means the particle has energy E3. Psi 4 means the particle has energy E4, of course, in the absence of degeneracy. So there is a concept of degeneracy in which multiple states can have the same energy level. So we'll keep that to the side for now. If there is no degeneracy, then out of all the possible eigenstate solutions of the Schrodinger equation for a given system, every single state is associated with a fixed energy level. It means that if we find out that the particle is in any one of these states, it simply means that the particle has any one of these energies. You know, in classical mechanics, if a particle is in a system, it has a continuous distribution of energy. The particle could be at rest, it could be moving with a medium velocity, it could be moving with a very large amount of velocity, a continuous distribution of kinetic energies. But in quantum mechanics, it doesn't have a continuous distribution of energies. It has discrete energy levels in which the particle can exist in, and this is a property for all kinds of separable solutions, for all situations in which we can represent the Schrodinger equation in this particular manner in terms of these separable eigenstate solutions. Now, what is the meaning of having a large number of eigenstate solutions for a given quantum mechanical system? Well, it means that the system could be in any kind of a state. We don't really know in what state the system actually is in. Only when we make a measurement do we actually find out in which state the system was actually in. And that is something very weird about quantum mechanics, because in quantum mechanics, the solution of the Schrodinger equation is a wave mechanical solution, right? And wave mechanical solutions has the property of superposition. I can add up wave mechanical solutions. So in a way, I can represent the general solution of a Schrodinger equation of a given system as a linear superposition of all the individual eigenstate solutions for that particular system. So let me show you, all right? So the third point that I want to discuss is the point related to superposition or the general solution for a system, the general wave function solution. Why do I say general? Because as I just now showed you, for a given system, the Schrodinger equation may lead to a large number of distinct solutions, also known as eigenstate solutions. So what is the general solution for a given system? You see, if I solve for a particular problem, I might end up getting that, let's suppose I have one eigenstate solution, I have another eigenstate solution, I have another eigenstate solution, and on, right? I call it psi 1, psi 2, psi 3, psi 4, on and on. Now these are eigenstate solutions which, if I combine with the time dependent part, then it simply becomes the wave function solution. So e to the power minus iota E1 t upon h cross. So E1 is the energy level associated with this state, and e to the power minus iota E2 t upon h cross. E2 is the energy level associated with this state, e to the power minus iota E3 t upon h cross. These are nothing but the wave function solution psi 1, psi 2, psi 3, okay, and on. So let's create a simple border here, okay, just to distinguish. So what the Schrodinger equation gives us is a large number of wave function solutions. So if the Schrodinger equation gives us a large number of wave function solutions, that means I can represent the final solution or the general solution for a system, because these are all quantum mechanical wave function solutions. And in my previous video, I have said, when I was trying to come up with the Schrodinger equation, that a Schrodinger equation has a property that its solutions follow the superposition principle. This comes from the imposition that the wave function solutions must have wave properties, and because waves can be added together. Therefore, the solution of the Schrodinger equation can also be added together. So in a sense, I can add all of them up to come up with the general solution, or we should say a linear superposition of all of them. So the general wave function solution is a linear superposition of all of these eigenstate solutions. I'm going to call as psi n e to the power minus iota E n t upon h cross. All right, and summation over n. This is known as the general solution of this particular system, whatever it is, whatever V we were dealing with. Okay, the general solution. So this is what the quantum mechanics offers us, is a general solution which is written as a linear superposition of a large number of eigenstate solutions. Now let us try to understand what this is. First of all, this is eigenstate solution. This is a time dependent portion, the function. Now this is Cn here. Cn is nothing but just a coefficient here. Now why have we applied a coefficient? We have applied a coefficient because the probability associated with getting one of these states is not the same always. Every state has a different probability that the system could be in that particular state. So for that, to represent that, we have Cn here. All right. So this is essentially the sum, the sum of, I can write in addition of all of these kinds of functions. So if I write it in this particular manner, so C1 psi 1x e to the power minus iota E1 t upon h cross, okay, wave function corresponding to the state 1, C2 psi 2x e to the power minus iota E2 t upon h cross, and on and on. Many cases we have infinite distinct solutions. Now I can further simplify it by writing it for at time t is equal to 0. So at, let's suppose, time t is equal to 0, I represent the wave function solution. This comes out to be x0. So here the time part e to the power 0, it vanishes. So I essentially end up getting summation over n Cn psi n x, which is nothing but C1 psi 1x plus C2 psi 2x plus C3 psi 3x, and on at time t is equal to 0. Okay. Now this is the general solution of a given state at time t is equal to 0, but and also known as the linear superposition of all the solutions. But what does it actually mean? It means that this is all the quantum mechanical theory can offer us. You see, when we deal with classical physics, we can actually solve the equations of motion to predict where the particle is exactly going to be, what is velocity going to be, what is its kinetic energy going to be. But in the quantum mechanical theory, we have a general solution for a Schrodinger equation for a system which consists of a large number of distinct states. All these states are mathematical functions, but these mathematical functions correspond to distinct energy levels, and these mathematical functions also have corresponding distinct probability densities, expectation values, etc., etc. So if I make a measurement on a given system, what is the answer that I'm going to get? Let's suppose if I take a hydrogen atom and I want to find out where is the electron, what is the energy of the electron, what is the prediction by quantum mechanics? The quantum mechanics simply says that the hydrogen atom exists before measurement in a superposition of many states. Okay, the quantum mechanical theory does not offer us a clear-cut answer of what is going to be the position or probability, position or momentum or energy of a state, but instead it says that before we make a measurement, the system exists in a superposition of states, and the moment we make a measurement, the measurement basically forces the system to reveal to us where it exactly is. So the hydrogen atom could be in either one state or two state or some other state, right? And every state being found has a certain probability associated with it. So quantum mechanics merely offers us a probability that if I make a measurement on a system, then what is it that I am going to get? This is very much similar to, let's suppose, throwing a dice. If I throw a dice, I don't really know what it is I am going to get. I might get 1, 2, 3, 4, 5 or 6. And every single side has a probability associated with it. So if I take a large number of dice and I just throw it randomly, then I cannot exactly predict which dice is going to be one-sided or two-sided or three-sided or three-faced, but I can know that if I make a large number of measurements, then I will end up getting a probabilities corresponding to each side, right? Similarly, if I have a large number of hydrogen atoms, then before making a measurement, I don't really know that in each of these hydrogen atoms, whether the electron is at a particular, probability density at a particular energy level or not. Before measurement, I don't really know anything. Before measurement, all the hydrogen atoms exists in a superposition of states. But the moment I make a measurement on each of them, every single hydrogen atom reveals to us that one atom is in a certain state, another atom is in a different state, another atom is in a different state. So in one case, the hydrogen atom might be in the ground state. In another case, hydrogen atom might be in the first excited state. In another case, hydrogen atom can be second excited state. Quantum mechanical theory cannot predict that if I make a measurement on a hydrogen atom, the atom is going to be in which state. What quantum mechanical theory offers us a kind of a statistical interpretation that the moment we make a measurement for a large number of similar hydrogen atoms, we know the probability of getting a specific state. That this many number of data will be associated with a ground state, this much data will be associated with first excited state, and on and on. So this is also known as the Copenhagen interpretation or the wave function collapse of a given quantum mechanical system, that the theory simply offers us an idea that the quantum mechanical system exists in a superposition of states, but the moment we make a measurement on the system reveals to us whether it is in state 1, 2, 3, 4 or 5. And all the quantum mechanical theory can offer us is a probability that if I will get this state versus some other state. So the wave function of the system has essentially collapsed into any one of the infinite solutions possible. This is known as the wave function collapse in the Copenhagen interpretation. Let me give you a little bit more detail here. Now, if I try to find out the expectation value of energy for the general solution, previously we found out the expectation value of energy for one eigenstate solution. But if I try to find out the expectation value of energy or the average energy for a general wave function solution, then I can simply say, okay, this is essentially equal to, I will take the general wave function solution, which is x. I think I will just take for at any given point in time, this is xt complex conjugate, and then we have the Hamiltonian for total energy and psi xt, all right, dx integrated over minus infinity to plus infinity. If I do this, what is this? This is essentially nothing but summation over Cn psi n e to the power complex conjugate. This should be complex conjugate iota E n t upon h cross, the Hamiltonian, and then you have summation over n C n psi n e to the power minus iota E n t upon h cross dx. Okay, these are different things. Okay, just small division. So here again these terms gets cancelled out. I can take the summation over Cn outside the integration, so I get a double summation over Cn modulo star Cn, and I end up getting psi n star h operator psi n dx. Now the moment h acts on psi n, we end up getting En. Okay, En is basically all the energy levels corresponding to different values of the n integer. So this is nothing but, I can say, okay, a summation over n of Cn mod square, and I have En integration of psi n star psi n dx. Now because the eigenstate solutions should be normalized to satisfy the Born statistical interpretation, so this overall comes out to be equal to 1. And I actually end up getting the average energy for a system overall with respect to the general solution is summation over Cn mod square En, which means that for different values of n, I have C1 square En E1 plus C2 square E2 plus C3 square E3 and on, which means what? It means that the average value of the energy for a given quantum mechanical system in terms of the general wave function solution is simply some number times individual energy levels which are allowed. Now what is this number? If you are familiar with probability theory, this number simply represents a probability that a system is in a given state, right? So this is nothing but the probability that a system is in energy level E1 times E1, probability that the system is in energy level E2 times E2, probability that the system is in energy level E3 times E3, and on. Now keep in mind that we have to ensure that there are a couple of things here. First of all, This is only true if the overall generalized wave function solution is normalized. Okay, so again, normalization is everywhere. So we must impose normalization on the general wave function solution. So normalization simply means that all these probabilities add up to 1. You know, the total probabilities that if I make any measurement, I will get some energy level, all adds up to 1. So that normalization simply means that the Cn square should all add up to equal to 1. That means that the summation over Cn square should add up to 1. So this is something that we must impose from our end, otherwise we might get different or wrong values of probability. So if I impose normalization of the overall generalized wave function solution, then suddenly we end up getting these probabilities that if any given kind of a quantum mechanical systems exists in a superposition of states, a linear combination of the eigenstates, then if I make a measurement, the particle will be in a given state, or the particle will have a given energy level, and those energy levels, or the particle being found in those energy levels, is associated with some kind of a probability. So if I make a measurement, what is the probability the particle will be in state 1 or will have energy level E1? It is simply C1 square. What is the probability that the system will be in energy level 2? Is C2 square. What is the probability that the system will be in energy level 3? Is C3 square, and on and on. So quantum mechanical theory can never really predict where the particle is, what is its momentum, and what is its energy level. It only offers us a linear superposition of states, and it is up to measurement to reveal to us where the system is actually going to be in. The only thing that we can know or infer is a probability that if we make a large number of measurements on similar systems, then a certain energy levels will have a certain ratio in that particular data. Now, one last point that I want to discuss before I finish this video. We have talked about normalization of an eigenstate solution. I want to talk about orthogonality. So in the coming lectures, when I'm going to be solving for different kinds of potentials, we will see that the eigenstates for different potentials, distinct eigenstates are orthogonal to one another. So what it means, I want to clarify that one last time. Okay. So whenever we try to solve the Schrodinger equation for a potential, we end up getting a large number of eigenstate solutions, right? These eigenstate solutions contain information about the particle's probability, density, energy level, etc., etc. And we impose the condition of normalization on the individual eigenstates as well as on the general solution, right? Both are slightly distinct normalization processes. This is a normalization process that has to do with bond statistical interpretation, that if I take psi n star psi n dx, this should give us to be 1 between minus infinity to plus infinity. Perfectly fine. Okay, that means the probability of the particle being found in the entire universe is equal to 1. But then there is another concept called orthogonality. Orthogonality means that if I take two distinct eigenstates, I take psi n and I take psi m, where n and m are not really the same, I do its integration from minus infinity to plus infinity, it comes out to be equal to 0. That's it. So if I take two distinct or separate eigenstates, their inner product essentially comes out to be 0. It means that they are orthogonal to one another. Now, orthogonality is a word that you must be familiar from vector algebra, where we think of two vectors as perpendicular to each other or being independent of each other. Here, there is no geometrical interpretation such as, but mathematically it simply means that two eigenstates are independent of one another. Alright, they are independent of one another. That means if a particle is in one state, just one state, it is not in the other state, or it won't evolve to be in the other state, as simple as that. And majority of the potentials share this kind of a property where their eigenstate solutions are both normalized as well as orthogonal to one another. So if I combine both these two conditions, so then we end up getting what is the condition called orthonormality, which means that if eigenstates are orthogonal and normalized, so normalization and orthogonalization will lead to orthonormalization, which means that psi n star x psi m x dx between minus infinity to plus infinity is equal to a Kronecker delta Mn. Now you understand what a Kronecker delta means. It means that this is equal to 1 if m is equal to n and equal to 0 if m is not equal to n. Just ignore these things. Okay. So if m is equal to n, we end up getting normalization. If m is not equal to n, we end up getting orthogonalization condition. So these properties, that whenever we have a potential in which the potential is independent of time, we can apply separation of variables method to get these separable solutions, also known as eigenstate solutions. Then those states, the solutions are stationary. That means their probability densities, expectation values are constant in time. Nothing really happens in these stationary states. And those eigenstate solutions, which might be a large number of them, correspond to distinct energy levels. So if I find out that one particle is in one state, it has a different energy compared to if it is in another state, it might have a different energy. All of them combined together in a linear superposition gives us a general solution for a system. And the quantum mechanical theory merely offers us the probability of the particle being in a given state if we make a measurement. And thirdly, they also, many cases, they share the property of orthonormalization. So that is all for today. In the next video, in the coming videos, we are going to be solving the Schrodinger equation for different kinds of potentials, and we will see that these properties kind of hold true in all those cases. I am Divyesh Das. This is all for today. Thank you so much. Take care. Bye-bye.